Hello everyone. Today I am going to talk about Skyhook DM, embedding Apache Arrow inside storage systems. So today's agenda is that I will start with discussing the broader problem that we try to solve and the solutions that already exist. Then I will discuss our approach and how is it different from the existing solutions. And then I will go over the background knowledge that is required to understand our implementation, and also go over the design and architecture, and then finally conclude with a brief performance evaluation of our system. So the broader problem. So with high-speed storage devices like NVMe SSDs serving up to 2 to 3 gigabytes per second, and with the introduction of high-speed networks in data centers supporting up to 25 to 100 gigabits, the bottleneck has moved from the I/O layer to the CPUs. So basically, CPU is the new bottleneck in today's high-performance systems. This issue is mostly seen in the space of data processing, where all the data is nowadays stored in highly efficient file formats such as Parquet and ORC, where a lot of encoding and compression goes into storing the data efficiently. Now the problem is that when trying to read and process the data on the client side, all this data first needs to be read to the client side, and then a lot of decoding and decompression has to happen, which is inherently CPU heavy task, and that causes the client side CPUs to get bottlenecked and leads to hampering the scalability and reduced latency and throughput. One of the ways that people use to fix this problem is moving to computational storage. So in computational storage, we try to offload as much compute as possible to the storage layer. So basically, we try to use the idle CPUs of the storage nodes to perform tasks like filtering out unnecessary data, doing decoding and decompression. So how this helps is that we can filter out a lot of unnecessary data and save a lot of network bandwidth, and basically just move the result data to the client, thus accelerating queries due to reduced data movement. And also, we can offload a lot of CPU wasteful tasks like decoding and decompression to the storage layer directly, so that the client nodes can do some actual computation. So all this helps reducing data movement and increasing and decreasing latency and increasing scalability. So how is our approach Skyhook different? So Skyhook basically tries to offload queries from the client to the storage layer. So it behaves as a computational storage system. But most computational storage systems out there require extra hardware support, like smart SSDs or SSDs embedded with FPGAs for offloading compute. Now, it is not always very trivial to acquire this sophisticated hardware. So what we try to do in Skyhook is that we try to move one level up from the hardware to the storage node and try to use the storage node's CPU to do compute offloading. So basically, we don't require any extra hardware and use the storage node CPUs to instantly start offloading from the client to the storage without any wait for acquiring sophisticated hardware. Now, we try to see if this approach works, what are the challenges, and what needs to be done to fix those challenges. Also, Skyhook enables compute offloading in existing programmable storage systems without any code changes. So if you have an existing programmable storage system deployment, you can basically start offloading instantly in that storage system if you follow the Skyhook approach, and basically test out computational storage performance with your existing storage infrastructure. Also, in Skyhook, we do not handwrite another new query engine of our own. Rather, we embed popular data access libraries directly inside the storage layer. So basically, this allows offloading a lot of metadata management, a lot of complex metadata management from the client to the storage layer, and the client do not need to know about metadata. So before going deep into Skyhook's design and architecture, let's start by discussing a little bit of background over the main components that build the Skyhook implementation. So one of them is Ceph, a distributed programmable object storage system, which has three types of storage interfaces: a POSIX file system interface, a S3-like object storage interface, and a block device interface. So now the main feature of Ceph is it does not have any central point of failure. So, this is because it uses an algorithm called Crush, which is basically a hash map kind of algorithm that maps objects to their locations in the cluster to the OSDs. Now, when a client connects to a Ceph cluster, it basically downloads the crush maps to it. And then while trying to do an IO to the Ceph cluster, it basically calculates the location of an object from the crush map and interacts directly with the storage server, bypassing any central point of coordination. One of the main features of Ceph that we use in Skyhook is its extensible object storage layer, which is Rados, and the presence of the Ceph object classes SDK that allows embedding user-defined functions inside the object storage layer to be able to modify objects in a user-defined manner in the IO path, in the object store IO path. Let's discuss about the Ceph object classes SDK in detail in the next slide. So basically, the Ceph object class mechanism is a plugin-based object storage extension mechanism. It allows extending the object store IO path with user-defined functions. So if you see on this figure, at the very bottom, there is the object storage layer, which has the chunk store and the key value store, and which basically serves raw blobs of data. Now, above the redundancy layer, there sits an object context, and we basically, using the object class methods, using the object class SDK, we can basically embed an object class method in this object context. So irrespective of the location of the replicas of the object, this object class method can modify the object inside the storage layer in user-defined manners in the IO path when the modifications to the object is basically happens in flight. The object class mechanism is actually used by a lot of Ceph internals, such as the Ceph file system interface, the Rados gateway S3 interface, and the Rados block device. The object class mechanism in Ceph is actually quite popular and is actually used by a lot of Ceph components already. And this graph shows here, over the years, the use of the object class SDK has kept growing in the Ceph ecosystem. Now, the second most important component, or another most important component in Skyhook is Apache Arrow. So, as most of the audience in this talk already might know about Apache Arrow, but still, Apache Arrow is basically an columnar in-memory format that is optimized for zero-copy operations on modern hardware. And basically, it allows for zero-copy data sharing between multiple data processing systems. So, for example, if you have multiple data processing systems talking to each other, without Apache Arrow, one needs to copy and convert data from one data processing system's format to another system's format. But with Apache Arrow, or rather with all the systems understanding the Arrow format, there can be only one copy of data in memory, and all the systems can directly interact with it without the need to do multiple round trips of serialization and deserialization. Now, although Apache Arrow project started as in-memory zero-copy format, it quickly grew to a rich collection of pluggable components for building data processing systems. So, for example, the Arrow framework provides a binary IPC protocol for transferring Arrow data over the wire. Also, it provides file format interfaces for scanning files of multiple of different kinds of file formats. Also, it has a file system interface for interacting with multiple local and cloud file systems, a datasets framework for abstracting over a set of files and doing dataset discovery, RPC framework for doing gRPC related calls, compute kernels for doing complex compute operations, embeddable compute engine, and much more interesting data processing frameworks. Now, for the Skyhook project, we use the components that that are marked with a black star here. And in the later slides, we will discuss how we put together these components inside Ceph to build Skyhook. So now let's discuss the design paradigm, the basic design paradigm behind Skyhook. So in Skyhook, uh, we extend the client and storage layers of programmable object storage systems with data access libraries. So as you can see in this figure on the right hand side, this is the object store layer of a object storage system, and we embed data access libraries directly inside the object store layer. Also, we use data access libraries on the client side to be able to interact with these libraries embedded inside the storage layer. Now, we use we use plugin based mechanisms similar to the object classes SDK in this design to be able to embed the data access libraries and to be able to invoke it from the client layer. Now, since these data access libraries are mostly designed to work on files in a file system interface and not over objects, we devised a file system shim uh, that can be embedded inside storage nodes and that can wrap objects to provide a file-like view over objects. So once there is a file-like view over objects, these data access libraries can be used out of the box to scan these objects as files. So now that we have a user-defined function embedding data access libraries inside the object store, we need some way to invoke it from the client side. So we basically use the direct object access interfaces of the storage systems to be able to invoke these user-defined methods on objects from the client. So what we need to do is that we need some way to make these object class extensions directly available to the clients without changing any code in either in the POSIX layer or in the direct object access layer. Now, if any pair of programmable object storage system and our data access library can adopt these three key points of the Skyhook design paradigm, then basically that pair of the storage system and the data access library can be used to build another instantiation of Skyhook. So now let's discuss about the file layout design that we follow in Skyhook. Now, in Skyhook's implementation with Ceph, there is a limitation that the maximum object size allowed by Ceph is 120 megabytes. So in this work, we use files that are 64 MB in size, as we found out that this provides the best performance due to Ceph specific reasons. So what we do is that when files are lesser than 64 MB, we just write it as it is. And if files are larger than 64 MB, then we take these files and split it into files of 64 MB size, of approximately 64 MB sizes. Now we ensure that each of these partition goes into a single Redis object. Now, why do we need to ensure that each of these partition go into a single Redis object? This is because we try to get a 1:1 mapping between files and objects that would facilitate the direct translation of file names to object IDs. So why do we need this direct translation from file names to object IDs? So as we discussed in the previous slide of design paradigm, that the data access libraries on the client side somehow need to invoke the user-defined functions on an object. But now the data access library on the client side is just having access to files in a POSIX file system. It does not know anything about objects. So during the read path, we need some way to take file names and convert it into object IDs, and then invoke the user-defined functions on those object IDs. So for doing this translation between file names and object IDs, we need to ensure this 1:1 mapping. You can see here in this diagram below how we split up a Parquet file and how we ensure that every Parquet file is self-contained within an object. So, for example, we take a Parquet file having 3 row groups and its own footer metadata. We take it, we split it into 3 smaller Parquet files, each having 1 row group and its local metadata, and then we make sure that each of these Parquet file goes into a single object. Now we discuss the architecture of Skyhook. So in Skyhook, there are two layers: the client layer and the storage layer. So on the storage layer, at the very bottom, there is the object storage layer, which serves blobs of data without any semantics attached to them. Now above the redundancy layer, there's an object context, and the object context has uh, embedded object class methods, which basically use Apache Arrow libraries to go ahead and scan these blobs of data. Now, since we use Apache Arrow, we can scan files or objects or rather objects of any format, such as IPC, LZ4, Parquet, etc. And all this scanning happens to a file system shim. On the client layer, there are two paths: the read path and the write path. On the write path, users just need to take Parquet files, split it accordingly, and then just write the Parquet files to the Ceph mount, and that's it. It's that simple. But on the read path, we have the dataset API, and using the dataset API, we abstract over the set of Parquet files that we wrote into the Ceph mount, and then uh, we launch scan tasks, where each scan task takes a file, converts the file into an object ID using the striping metadata from the Ceph, and then invokes the object class method on that particular object ID. All the query parameters and the filters and projections are basically serialized in form of flat buffers and sent uh, through this query execution call. Now, after the query execution call invokes the object class method, the scanning happens. We get a result arrow table. Now, the result arrow table is serialized into an where format, and then it is sent back to the client in binary IPC format. So this is how one would use Skyhook from Arrow. In general, using the dataset API, if you want to scan a dataset containing Parquet files, you do something like this. You basically instantiate a format Parquet, and you just provide the format argument to the dataset API and mention the dataset, and that's it. But for using Skyhook, it's also really simple. And we have devised this Skyhook file format abstraction, which is basically a virtual file format that can offload scans to any real file format, such as Parquet, Feather, IPC, whatever. And what we need to do is we need to wrap the Parquet file format with the Skyhook file format. And we, instead of providing Parquet, we just need to provide this Skyhook file format in the dataset API, and that's it. We can go ahead and scan files by offloading them to the storage layer. And since Skyhook is tightly using Arrow, we can support scans of any file format that Arrow supports out of the box, such as Parquet, CSV, JSON, Feather, etc. Now let's go ahead and discuss some performance evaluations that we did with Skyhook. So let's start with some query latency experiments that we did. So basically, we took a data set and did some experiments to select 1%, 10%, 25% of the rows. Or like we did row selectivity experiments starting from 1 to 100%. And we scaled out our experiment from 4 to 16 nodes. So in our row selectivity experiments, we found out that Skyhook scales with the cluster size, but Parquet does not. It stops at a point. So we also found out, for example, in the 4-node scenario, when Skyhook cannot benefit from the scale out because Parquet already have enough resources, or the client-side execution already have enough resources to scan data from 4 nodes, then the serialization overhead of Skyhook dominates. The serialization overhead is basically the overhead of packing an in-memory result arrow table into the where format, where all the column buffers need to be copied separately and where together contiguously for sending them over the network. Also, you might say the 100% selectivity of Skyhook results in an results where you might see that Skyhook is slower than the without Skyhook case. This is because for 100% selectivity, Skyhook results in an unnecessary packing and unpacking of the data inside the storage nodes. So basically there is no fast path. But this is not a problem because we can simply detect the 100% selectivity queries and just avoid offloading to Skyhook altogether and just can scan on the client side using Parquet. We also did CPU usage experiments, where in this plot we show the client side results in the thick blue line, and all the other thin lines show the storage side results. So we show that Skyhook provides compute access to all the CPU resources in the system, thus improving scalability and performance. Whereas with Parquet, the CPU available to the client side scan is only limited to the client side, to whatever CPU is present on the client side. There is a little bit CPU utilization on the storage side while using Skyhook. On the client side, while using Skyhook, this is because Skyhook sends data in the form of LZ4 compressed arrow batches to compete with the Parquet binary format, and thus the decompression of the LZ4 compressed batches on the client side uses up some CPU on the client side while using Skyhook. So we can generally say the simplicity of offloading using storage node CPUs trades off the total CPU usage. But we end up getting better performance and much more scalability just by giving up a little more CPU. We also did some network traffic experiments where we found out where we did experiments with 100%, 10%, and 1% selectivity. And we found out that Skyhook prevents unnecessary bandwidth wastage, making room for other applications. So for example, if you see like the 10% and 1% selectivity queries, without Skyhook, all the data ends up getting moved through the network unnecessarily, thus clogging the bandwidth. Otherwise, with Skyhook, only the required amount of data is moved through the network, and that saves up a lot of network bandwidth for other applications. You can see the bandwidth usage during the 100% selectivity case in Skyhook is a little more than without Skyhook. This is mainly because in Skyhook, we send the data back in LZ4 compressed arrow IPC format, which is a little more inflated than the Parquet binary format. We also did crash recovery experiments with Skyhook to find out how fault tolerant are Skyhook queries. Now, since in Skyhook, the compute is tightly integrated with the storage layer, the fault tolerant semantics of the storage layer apply to Skyhook and makes the Skyhook queries automatically fault tolerant. So basically, when a server crashes and restarts, irrespective of the new positions of the objects in the restarted server, since the object method calls that we use are above the redundancy layer, the object method calls just simply restart on the new location of the object, and the Skyhook query is just complete till the end correctly. We ended up implementing ended up upstreaming Skyhook inside Apache Arrow, and you can go ahead and see and basically try out Skyhook. And there are 2 blogs that we wrote, which are linked here. This will give you a quick getting started guide on how to use Skyhook from Apache Arrow. Some future work that we plan to do in the coming months over Skyhook is that first we need to fix the memory to wire serialization overhead. This can be done by RDMing the column buffers directly from the storage to the client, thus doing a 0 copy transfer. Also, the current version of Skyhook uses the Arrow Dataset API for doing the selection and projection inside the storage layer. We aim to move to the Arrow streaming compute engine to take benefit of the streaming interface for performance, and also to take benefit of being able to execute much more complex operations that Arrow supports, such as group buys, aggregations, other string operations, etc., rather than just supporting a simple selection and projection. Also, we aim to use Gandhiva inside Skyhook to be able to accelerate Arrow query processing and to be able to fully leverage the SIMD processing capabilities of modern processors. So that's it. Thank you very much for listening to my talk. If you have any questions, please shoot me an email on this email address. And thank you. Have a great rest of the day.